Hello everyone and welcome to this video where we will talk about the normal law a second time. In the previous video we saw the description of a continuous probability distribution and of a continuous random variable in general, and we introduced the standard normal law and the normal law itself, but we worked more on the standard normal law and especially using the table of this normal law. So now we're going to work with a given normal law with some parameters that are a mean and a standard deviation that are not always, of course, 0 and 1. So let's say that at the first step, we are able to change our normal law with its parameters to a standard normal law with the parameters 0 and 1. So let's see an example and let's see the comparison between both laws. Taking here the normal distribution with a mean of 25 and a standard deviation of 10, the curve is what appears. So in this normal law, we would like to calculate the probability of x on the horizontal axis is less than 30. So it corresponds to some area, that is this one, colored in pink here. And we obviously don't know the value of this probability only by looking at the graph. So one first possibility is to translate this problem into the standard normal law. For it, we've got a table of values of probability. The second method consists in using the normal law tool of the calculator and getting a direct result only with this problem and without any other tools. So in the standard normal distribution with 0 at the center, so as an average value, and with 1 as a standard deviation, we are just seeing that the scale of the horizontal axis just changed in comparison with the scale of x, of our variable. And of course, the scale of the vertical axis is changing as well, because the total area for both curves always equals 100%, so 1. But it's not very important, okay? The vertical values are not very important. What is important is to be able to translate this question with respect to some value of x in one question with respect to the value of u, that is the name of the value of the standard normal distribution. By the way, you will find in many books z as this variable. Okay, so it can be named u or z. Sometimes this variable of n01 is named t, but it's some kind of mistake because t refers to the student distribution, and we don't have to make any confusion between a normal and a student distribution. So you can use u or z or z. With the law n01, this probability is some probability on the value of u. So I'm putting in color the same area as the one on the left. And my question is, where do I have to stop on the u axis in order that the probabilities are the same? And we can guess, because we've got the graphs in front of our eyes, that it could be 0.5. But why 0.5? So let's put in parallel both axes and a third one referring to the general notation of each values. At the center, we've got the mean, mu. And we can notice here that if we go from 0 to 1, we just added one standard deviation to the mean. So mu plus sigma. And if we go to the value 2 of u, we just added two standard deviations to the mean, and so on. So we can guess that the scale -3, -2, -1, 0, 1, 2, 3 is actually the general scale that appears here, and that will help us to translate it into the x values, where the central value is 25, and where adding one standard deviation means adding 10. So the values that correspond or that match the values of u are for x 5, 15, 25, 35, 45. And for 3, it would be 55, and so on. So we've got a correspondence between values of u and value of x. Now, our value of 30 will be translated, okay? We are allowed to translate it because we can notice that if we stop at 30 on this axis, we just added a half of the standard deviation from the mean. And what does it mean on the u-axis? Adding the half of the standard deviation to 0 leads to 0.5, of course. So it would be a good idea to have a general formula to give us the right value of u, whatever the value of x, and without trying to guess by ourselves how many standard deviations were added or subtracted to the mean. So it's just a question of logic. If you subtract 25 to 30, you've got the value 5. And if you divide it by the standard deviation, that is 10, 5 over 10 leads to 0.5. So it could be, and it is actually a good formula to calculate the value of u, starting with a value of x. Of course, this formula can be transformed in order to make us get the value of x if we know already a value of u. Okay, u times sigma plus the mean leads to x. So x is the mean plus u times sigma. But for our problem, we have to get a value of u thanks to a value of x. This value of x is 30. We just have to subtract 25 and to divide by 10. So the probability of x is less than 30 is the probability of u is less than 30 minus 25 on 10. So the probability of u is less than 0.5. And this probability can be found directly on the table of the standard normal law, as in the previous video. So now, let's apply it in exercises with exercise 17. So we're taking here the law n5010. And so the variable change formula tells you that you will have to calculate u equals x minus 50 on 10. You can notice that I put uppercase letter here and lowercase letter here. So it's because this formula is a general formula on the variables x and u, and this calculation calculates some value u on the variable u and some value x on the variable x. So as always, a variable is put in uppercase letters in statistics and in probabilities, and a given value of one variable is the lowercase corresponding letter. So now let's go back to our exercise. We would like to calculate, this is a scheme that is not important in the exercise, just to illustrate our problem. We would know what is the probability of x is less than 60 in this law. So let's translate it in the standard normal law by calculating the value of u. So it will be 60 minus 50 divided by 10, so 1. And P of u is less than 1 can be read directly on the table, 0.8413, so approximately 84%. Next question, the probability of x is less than 43. 43 leads to this calculation for the variable u, and then this result, negative 0.7. You can't read the result directly on the table. You have to transform this writing. So the rule of the two transformations. Okay. The sign is less than has to be kept, but a negative value has to be transformed in a positive value for the form. And then you have to apply a second transformation. So it will be P transformed in 1 minus P. So this probability is equal to 1 minus P is of u is under 0.7. This second probability can be read and the calculation can be finished and leads to the result 0.242. Let's calculate the probability of x is between 45 and 55 in this law. We can translate two values of x into two values of u. There is no problem about that. Just calculate twice with this formula. So 45 minus 15 on 10 and 55 minus 50 on 10. The results are negative 0.5 and 0.5. So we can now cut this formula that corresponds to an interval of real numbers. So it's P of u is less than 0.5 minus P of u is less than negative 0.5. The first one can be read on the table, not the second one that has to be transformed in 1 minus P of u is less than 0.5. So P of u is less than 0.5 appears 2 times in the calculation. That's why a 2 here. 2 times P of u is less than 0.5 minus 1. That will be the result of the transformation of this writing, and the numerical result will be 0.383. So here is how to apply a variable change if you want or if you need to use the standard normal law. You need to use the standard normal law in problems where there is a parameter that is missing in the first normal distribution, and where you already know a result on a probability. So this result can help you to find the correct value of u that corresponds. And then by putting this value of u in the formula, and by knowing the value of x, you will be able to calculate the missing parameter that could be the mean here or the standard deviation here. Okay, so you've got reversed problems that correspond to a lot of problems, actually, where you would be obliged to begin with the standard normal law, use this formula, and go to your normal law. But in this exercise, you weren't obliged to do all of that. You could have asked to your calculator the probability that has been asked and to do it directly. So in the next slide, we will see it how. Using your calculator with exercise 17, sorry, with the Texas and with the Casio, lead to this writing for Texas and this one for Casio. So let's decrypt this writing. First of all, you have to use the right tool and to go on the tool. So in a Texas, you have to press the keys second var to have access to distributions, and then in the list of distributions, you have to choose normal f rep. So that is in the normal distribution, the fact to calculate the probability to be in an interval. And don't make a mistake, but this is an interval minus infinity, sorry, to 60. Okay, if x is less than 60, means x belongs to minus infinity 60. You can't enter minus infinity in a calculator, so you just have to enter a large negative number to simulate minus infinity. So you could have put 10,000 or 1 million, whatever. The bigger it is, the better it will be for your result. Okay, with these parameters, negative 1,000 is very, very good. Okay, it's far enough for us. So you have to put your interval in the function and then to put the parameters of the law. And in the Texas, it will work and give you the correct result. That was, I guess, 0.8413. Okay, that was your result, that approximately 84%. On Casio, this will be the same thing approximately, but Casio asks first the standard deviation and then the mean. So you have to reverse the writing of mu and sigma in Casio. Norm CD can be reached with the key option and then the item on screen stat and then the sub-item dist, option stat dist. Then you have to choose norm for the normal law and then NCD for normal CD. That corresponds to normal FREP for the Texas. That means a probability to be in an interval. For the second question, it will be obviously the interval 43 plus infinity. Okay, is more than 43 means belongs to 43 plus infinity. And at last, the parameters of your law. If you've got an interval with real numbers, two real numbers, you just have to put them as an interval, of course. 45, 55, 50, 10. And 45, 55, 10, 50 for occasion. Okay, so it's very direct, quick, and simple on a calculator to ask for a probability in the normal distribution. But you have to avoid mistakes by entering parameters on your question. Now, let's see a last part for the descriptions of the normal law. That is named here transition to a normal law. So the question is, how could we use a normal law instead of a discrete distribution that could be a binomial one, for example? Would it be relevant to do it? And how to do it? Well, let's recall and have reminders on the general scheme of discrete distributions that we studied earlier. That is hypergeometric distribution, so a Bernoulli scheme without repetition, binomial distribution, Bernoulli scheme with repetition. That corresponds to a probability of success that is a constant, whatever the number of trials. We've got the fact that it's been possible to use a binomial distribution instead of a hypergeometric one if the size of the population is more than 20 times the size of the sample. We saw that we could use a Poisson distribution if three conditions were met. So n is more than 30, p is less than 0.1, and np is less than 10. So you can use a Poisson distribution with a parameter that equals n times p, that we already know from the binomial distribution. And that was the expectation of the binomial distribution. So the parameter of a Poisson distribution is this expectation, and it's its expectation. So now what can do the normal distribution for all of that? Well, we saw in the previous video, in the first slide, the very first of the previous video, that there was a convergence of discrete distributions, at least those that appear here, to a normal distribution as n tends to be big. So it could be useful to use a normal distribution instead of a binomial distribution or a Poisson distribution, and of course instead of a hypergeometric distribution, by following the arrows. First, you can jump to a normal distribution from a Poisson distribution if its parameter is more than 20. But it's in contradiction with this criteria. These criteria. Okay? If lambda is more than 20, it means that n times p is more than 20. But the condition to go from here to here was n times p is less than 10. So you can't follow this path, okay, if you come from a binomial distribution. It appears that some other situations can lead to a Poisson distribution where the parameter that is not np could be more than 20. And if it is the case, you can use a normal distribution instead of a Poisson one. But you can use a normal distribution instead of a binomial distribution. Oh, by the way, coming from a normal distribution, of course, the mean will be lambda. Lambda is always the expectation of the Poisson distribution. And by the way, again, lambda is the variance of a Poisson distribution, and so the standard deviation will be the square root of lambda. Then, for the normal law that has been created, or that has to be created, mu equals lambda and sigma equals the square root of lambda. So now, coming from a binomial distribution directly, there are criteria to be met. First, n must be more than 30. So I put here more than, and here more or equal to, more than or equal to. So it's not very important. It could be more than or equal to at this location as well. It's just some limit that is chosen, not at random, but almost. So you have to check this point because it's a rule that has been chosen. The second one is that n times p must be more than 5. So it's almost in contradiction with this point, okay? N times p is less than 10. So here n times p couldn't be too big in order to go from binomial to Poisson. And this way, n times p has to be big enough to go from binomial to normal. And at the same time, n times q must be itself more than 5. So q being, of course, the complement probability of p. So if p equals 20%, for example, q equals 80%. So this way, you can create a normal distribution and its result will be close to the results of a binomial distribution with parameters that are obviously mu equals n times p. Okay, so the expectation of the binomial distribution. And what was the standard deviation of the binomial distribution? The square root of n times p times q. So you will have to calculate it to create the standard deviation of your normal distribution. So that's the first point. All of that. Normal distribution can be obtained from a binomial one or a Poisson one according to criteria and by calculating its parameters with the former parameters of the former distributions. But the problem is still a normal distribution works with a continuous random variable. So values that can be all the real numbers in some interval. But these distributions work with a discrete random variable. That is a number of successes, that is, no, 1, 2, 3, 4, so positive integers or non-negative integers. Okay, it could be 0. So there remains a problem, and you will have to be very, very careful when using a normal distribution instead of a discrete distribution. So the normal distribution can be directly used coming from continuous concrete situations where the values of x are size of objects or mass of objects or durations and so on and so on are typically continuous and real variables. Now, Bernoulli scheme, binomial or poisson leads to a bar diagram. Each bar showing with its 8 the value of a probability and targeting at the bottom an integer at the value of x. So we could think about 0, 1, 2, 3, 4, 5, and so on. A normal distribution is represented by a curve on a graph, a curve of a continuous function, okay, defined on R, and in a special concrete case, at least on a certain interval of real numbers. So how could we translate this kind of graph into this kind of graph, or to be able to talk about this kind of graph? Well, each integer has to be transformed in an interval that is around an integer on this graph. And of course, if you want that each integer has the same weight compared to each other, you have to create intervals that have the same size. So going to the semi-integer on the left to the semi-integer on the right. So to represent the number 16 as 16 successes in a binomial distribution, you have to talk about the interval 15.5, 16.5, whose or which area will represent the probability to be equal to 16. Okay, the probability of 16 successes. So you will have to ask your calculator with a normal distribution, the probability to be between 15.5 and 16.5. The probability to be equal to 17 successes will be, for the normal distribution, the probability to be between 16.5 and 17.5, and so on, for each single value of number of success. Okay? It doesn't correspond to what to do with continuous concrete situations. It only corresponds to what to do coming from a concrete or not discrete random variable. A last example of reading this kind of graph. If you want the probability to have less than 16 successes, you have to stop at the blue interval here, or the blue area. So at the beginning of this blue, you don't have to take 16 into account. So the probability of less than 16 successes is, for the normal distribution, the probability of x is less than 15.5. If you stop at 16 in your demand on your calculator, you will count approximately the half of the probability of 16, but you don't want the outcome 16 in your question, okay? You have to stop at 15.5. So let's illustrate it in the next video on some exercises. But let's see an example here in the next one. So with exercise 18, the exercise 18 has not been written here on the slide. So let's just say and describe the case here. You've got companies in a region, in a large region of a country. So you can guess that there are a lot of companies in this region. Okay, in this region, 30% of the companies do exports. Okay, now you're coming to take at random a sample of 80 companies in this region at complete random. And your purpose is to, not to guess, but to calculate probabilities of the number of companies that will do export inside your sample of 80 companies. Given that in the population, again, 30% of the companies do export. So your variable X is at the beginning the number of companies that will do export among the 80. And of course, you're asked to create a first distribution, okay, a probability distribution for X. So the point is that you are in a Bernoulli scheme at the beginning. Each time you choose a company, it will do export or not, and the probability of success is 0.3, and the probability of failure is 0.7. Okay, because in the population, 30% of the companies do export. Now, you have to ask yourself if you are choosing several companies at random with possible repetition or not. And in fact, if you are asked to choose at random 80 companies, the draw is without repetition. So you are running to a hypergeometric distribution in the end. But let's say till now that the total size of the population is considered to be big because the exercise didn't mention the size of the population, so the total number of companies into we have to choose. And the exercise tells you that it's a big region, a large region of a country. So you can guess that the total number of companies that are available is much bigger than 80 and bigger than 20 times 80. That would be 1,050 or 1,600 companies. Okay, so you have to tell that your hypothesis is that there is more than 1,600 companies in this region in order that the hypergeometric distribution can be treated by a binomial distribution. The translation in terms of probabilities is that your probability of success will always be approximately 30% each time you choose a company, even if each time it's a new company, and even if the size of the population is decreasing, as long as you choose companies. So P is considered here as invariable, whatever the company, because of what I just explained. Then your variable will be the random number of success or success companies among a random sample of 80 companies. So you are counting successes thanks to the variable x, and that's exactly what you need in order to talk about hypergeometric or binomial distribution. So this way, with a p-value that is constant, you go to a binomial distribution. And more precisely, the number of draws is 80, and the probability of success is 0.3. Now, second question, could we use a normal distribution instead of this binomial distribution? That could be used too. Okay. And what normal distribution? So let's see the criteria. Is n more than 30? Yes, it's 80. Is n times p more than 5? Yes, n times p is 80 times 0.3. 3 times 8, 24. It's more than 5. And is n times q more than 5? Yes, is if n times p is more than 5, n times q will be more than 5 because q is more than p. Q equals 0.7. But we could calculate it, of course. But 80 times 0.7 equals 56. So it's more than 5. So yes, normal law could be a good approximation to the binomial law that is here, with the parameters n times p for the mean and the square root of n times p times q for the standard deviation. So n times p times q is 24 times 0.7, that is 16.8, and the square root of 16.8 is indeed approximately 4.1. Okay, now our first question is what is the probability that the number of companies that will do exports in the 80 is more than 30? More than 30 successes means at least 31 success. So, as I told you earlier, if you want to use the normal distribution, you have to begin at 30.5. Okay, more than 30 means you can't consider the interval that is around 30, that goes from 29.5 to 30.5. So more than 30 is 20.5 to infinity for the normal distribution. And of course, you could check this kind of result, or let's display for occasion. You could check this result and compare it to what it would have been obtained with a binomial distribution. More than 30 success is the same as 1 minus the probability of at maximum 30. And at maximum 30 corresponds to a 2 in your calculator with the binomial tool, BCD for Ocasio and binomial FREP for Texas. And you could perform the calculation and just do it. And if you encounter a problem, of course, don't hesitate to comment below the video. The result, according to the normal distribution, is this one. Taking into account the binomial distribution, you will have a slightly different result, okay? But it mustn't be very far from this result. It has to be very close, okay? So, now let's answer the question, what is the probability to have exactly 30 companies that do export inside the 80? So, to be equal to something is a possibility in a binomial situation. And of course, having 30 successes is a possibility among others in our situation. But for the normal distribution, being equal to 30 is meaningless. So you have to translate it into an interval again. And for a normal distribution, being equal to 30 will be, coming from a binomial distribution, being between 29.5 and 30.5. But there is another tool on your calculator that could help you to calculate this probability maybe more directly if you target the value 30. You just have to choose normal FDP instead of normal FREP or normal PDF, sorry. It depends on the Texas. FDP or PDF is the same. You just have to mention the value 30 with these two, and then the two parameters of the law. Okay, so normal FREP is here to make you give an interval. Normal PDF is here to make you target one value if you come from a discrete situation, okay, a discrete random variable. So everything has to be taken into account at the same time, and that is the difficulty here in this part of the chapter. Okay, don't forget any point, otherwise you will make a mistake and have a wrong result. So on Ocasio it will be exactly the same. The corresponding functions are norm CD for an interval and norm PD for a value. So last example, let's see what we can do, and it will be quick, if we want to go from a Poisson distribution to a normal one. So let's take a variable that follows the law P of 25. So lambda equals 25 is the parameter that is at the same time the average value of the law and the variance of the law. What is the probability that x exceeds 28? So, of course, with the Poisson tool of your calculator, you can obtain this probability. Okay, with for Ocasio, for instance, Poisson CD with 28, you can get the probability to be less than or equal to 28. And of course, the probability that is asked here is the complement probability, so 1 minus the former result. But let's create a normal distribution and ask for a probability this way. So with the Poisson's law, your result would be 0.2366. So let's see with the normal distribution. So the criterion that has to be met is lambda is more than 20. And yes, it's true because here lambda equals 25. So we can use the normal law and 25, 5 lambda square root of lambda. In this normal distribution, we can ask this probability with, of course, the normal tool of your calculator with the interval 28.5 and 1000, for example. So to simulate the interval 28.5 plus infinity. And your calculator will give you the result 0.242. So 24.2% in comparison with 23.6%. But if you had made a mistake and put the value 28 instead of 28.5, your probability would have been maybe 26%. And it would be far from the true value that is here, actually, 23.66%. So you would have seen that you had made a mistake, okay? If your result is very close to the right one, you can think that you didn't make a mistake. Okay, so you will find in first time a video of exercises in French. I don't know when, okay, I can and I will have time to make a video of exercises in English. So you can find them in French, and it's better than nothing. So thank you, and see you for the next video where we'll talk about sampling and to use the normal law as a tool for other things. Bye.